Okay, today is the first of 2 weeks that we're going to spend talking about chemical kinetics. And in chemical kinetics, we are looking at and studying the rate of reaction. And the rate of reaction is the change in the amount of reactants or products or both as a unit of time or per a unit of time. And so when you have a chemical reaction occurring, and in this case, we're talking about the decomposition of hydrogen peroxide, you start at time 0 with a certain concentration of peroxide. And then over a period of 6 hours, you lose 0.5 or half of the amount of peroxide. So at time 6, you have 0.5 moles per liter. And if you look at this in terms of moles per liter per hour, it's 0.0833. Then in the next 6 hours, you lose a half again, and the rate of decomposition then decreases by approximately a half. And over the next 6 hours, you lose a half again, and so forth. And so the rate of decomposition of hydrogen peroxide decreases as the concentration of hydrogen peroxide decreases. And so a rate expression or a mathematical representation of this change over time can be written based on the concentration of the species involved. And it would look something like this. Here's the equation. You have 2 peroxides converted to 2 waters plus oxygen, and the rate would look something like this. The concentration at time 1 subtracted from the concentration at time 2 divided by the change in time, which would look like this. The rate would equal the change in concentration over whatever time period you are looking at. And if you were to graph the previous table, it would look something like this. The dark solid line would represent the concentration at any particular point, the y-axis being the concentration, the x-axis being the time. And you can see because at each point the rate is decreasing, that it becomes a curve which decreases in slope as you go down. Now, from this, you can derive 2 different measures. One measure is the average rate. And the average rate is the concentration. You use the concentration at time 0 and the concentration at, say, in this case, time 24, which is when we've ended, or the period. And using those 2 concentrations, you make a calculation over that 24-hour period. Or you can use find what's called the instantaneous rate. And the instantaneous rate is shown here as the slope of this curve at any point in time. For example, here we're at time 12, and the slope of this line, which is the change in concentration over the change in time at this one point, would be the instantaneous rate at this time. Up here, it's the instantaneous rate at time 0. And as you can see, the slope decreases, so the instantaneous rate decreases over the time period. Whereas the average would basically be the slope of a line that would connect 0 to 24. And the initial rate is this rate at the beginning or at time 0, which is generally, since the concentration is the highest, it generally represents the highest rate or highest chemical reaction rate. So here's another reaction. We have 2 times ammonia gas goes to form nitrogen gas plus 3 hydrogen gas molecules. So that's 2 molecules of ammonia break down to form 1 molecule of nitrogen and 3 molecules of hydrogen. Now, if you were to express the change in concentration of nitrogen, or I'm sorry, of ammonia over time as a function of nitrogen, you know that for every 2 molecules of breakdown here, you get 1 molecule formed here. And so the nitrogen would form 1/2, 1/2, as rapidly as the ammonia breaks down. And that's what this shows here, is the rate at any point of the breakdown of ammonia is, if you take that by -1/2, you get how rapidly the nitrogen forms over the same period of time. And so if you were to express the accumulation of nitrogen in this way, and you wanted to find ammonia, you would multiply this by 2, because you get 2 molecules of ammonia for every 1 of nitrogen. Now what would happen with nitrogen, and in other words, if you were going to relate the formation of nitrogen with the formation of hydrogen, well, you would guess that since it would be a 1/3 or 3/1 ratio, and sure enough, the formation of hydrogen, if you go this from left to right, it's going to be 1/3. The rate of formation of hydrogen is going to be, if you take that by 1/3, you get the rate of formation of nitrogen. So this graph shows all 3 of these relationships together. First of all, you have the line that represents the breakdown of ammonia, and it has its certain rate. Then you have a line that represents the accumulation or formation of nitrogen, and a line that represents the accumulation of hydrogen. And you notice that the breakdown of ammonia is faster than the accumulation of nitrogen, but slower than the accumulation of hydrogen, and that the accumulation of nitrogen is also considerably slower than the accumulation of hydrogen. And so if you were to take any particular point, and in this case, in this diagram, they've taken time as equal to 500 seconds, so at this line, and you were to draw slopes, instantaneous rates at those times, if you were to take the rate of formation slope of nitrogen as the baseline, then the slope of the ammonia would be 2 times the slope of nitrogen, and the slope of hydrogen would be 3 times the slope. And if you look at the numbers, here the slope's 9.7 times 10 to the minus 7. If you multiply that by 2, you get approximately 1.94 times 10 to the minus 6. And if you multiply this same number by 3, you get approximately 2.91 times 10 to the minus 6. Now obviously it's not exactly that way, but that shows the relationship is 1 to 2 to 3, which is consistent with the coefficients that are seen in this equation. So let's look at a problem related to this. So the first step in the production of nitric acid is the combustion of ammonia. So it's 4 ammonia times plus 5 oxygens equals 4 nitric oxides, nitrogen monoxide, and 6 waters. Write the equations that relate the rates of consumption of reactants and the rate of formation of the products. So how do we go about doing that? So what we would do is, first of all, you know that 1/4, which is going to be this, times the change in concentration of ammonia over delta T is going to equal minus 1/5, by the way, this is a minus sign because these two are being decomposed. The change in concentration of oxygen over time, delta T, and that's going to equal 1 over 4 times the change in concentration of nitrogen monoxide, and that's going to equal 1 over 6 times the change in concentration of water over time. And so you can leave it, this represents exactly what they're asking for here. This is the mathematical relationship of these four. At any particular time, you see that this is the relationship that you'll have. Now the second problem here says write the equation that relates the rates of consumption of reactants and formation of products for this. And it's going to be exactly the same approach. You're going to have the destruction 1 over 5 for this times the change in concentration of the bromide ion over time is equal to minus the change in concentration of BrO3 minus over time, it's 1 over 1 in this case, is equal to minus 1 over 6, the change in concentration of hydrogen over time. And then that's going to equal 1 over 3, change in concentration of bromine over time. And that's going to equal 1 over 3, the change in concentration of water over time. So it's pretty straightforward. You take the coefficients that are in the equation and you put them in these various ratios. Now let's look at one more problem. It says the graph in figure 12.3 shows the rate of decomposition of peroxide over time, and we have this. Based on this data and the instantaneous rate of decomposition at time this determined to be this amount, what is the instantaneous decomposition of these other two products? Okay, well, remember we said that 1 over 2 times the change in concentration over peroxide time is equal to 1 over 2 change in concentration of water over time is equal to 1 over 1 delta oxygen over time. So now what they tell you here is that the instantaneous peroxide rate at this time is 3.20 times 10 to the minus 2 moles per liter per hour. And that's for this species right here. So what would be, and it's asking what is the, at the same time point, what would be water and what would be oxygen? Well, the relationship here is the same, and so water would also be 3.2 times 10 to the minus 2 mole per liter per hour. And the relationship here is 2 to 1, and so this would be divided by 2. So it would be 1.6 times 10 to the minus 2 mole per liter per hour. So this forms at this rate, this forms at this rate.